So hello everyone.
Hey guys.
We're gonna talk about C.4 today, which is solar energy.
Yeah, so we're just gonna run through a PowerPoint and point out some key facts that IB wants us to know from the curriculum specifically.
hmm And we'll also just kind of explain a few things a little more in depth, and then also cover one of the questions from the textbook. Just the one because the others you can really get the answers from the rest of the slideshow on your own anyway, so we didn't think that would be very helpful.
Yeah.
Yeah. C.4, solar energy, which apparently includes biofuels. That's a great subtitle, don't you think? I just never got around to changing it. Anyway, part one is colored compounds and photosynthesis. Yeah, you can read that on your own.
Yeah, so chromophore. Pretty basic, but one thing that IB wants us to know is simply that light can be absorbed by chlorophyll and other pigments, the conjugated electronic structure. So that is the key point from this slide.
Yeah. And then if you want to clarify conjugated electronic structure or conjugated systems, I suppose, it's essentially, this is that's the wrong pen. You notice how there's 1, 2, 3, 4, 5, 6 double bonds here, and they each have the one single bond in between, and so because they're alternating, it's a conjugated structure. And this one has 6.
And this slide just goes just a bit more in depth.
Yeah. A few more examples. We've got retinol, which is essentially vitamin A. Purprin is interesting because of the conjugated structures and how it changes in different acids and bases. It can change color depending on pH, which I thought was interesting. Here's the actual chlorophyll, which is the main bit that IB wants you to know, I believe. And so chlorophyll A has a methyl group right here, while chlorophyll B has a CHO group. And this is the part where they don't absorb light, and so they look green.
And so this is the formula that you've probably seen before. It's quite common, but basically I just want you to know that this is the formula that tells you how photosynthesis converts light energy into chemical energy.
And just to clarify, light energy is this arrow here.
Yep.
Sunlight that causes the photosynthesis, and then the chemical energy would be referring to the glucose here because that's what your body runs on.
Yeah.
Did we cover? What was it? There's something else. Oh, yeah. So sorry about that. During the process of photosynthesis, the electron gets excited because the chlorophyll absorbed the one electron from because the photon that was absorbed excites the electron, right? And so through a long series of chemical processes, and it says that right on the slide. Please ignore me. Moving on. Biofuels. Yeah. God.
Yeah. So this slide goes over basically fermentation. And so what IB wants you to know is that the fermentation of glucose produces ethanol, which can be used as a biofuel. And this is the formula that demonstrates that. So far, I think these are the two main formulas that we're going to have to know.
No, plus that other one. That's coming up.
Oh, yeah, one more.
Yeah. And here's biodiesel. Was there something here?
Yeah, and so basically in this slide, the key point to take away is that the energy content of vegetable oils is similar to that of diesel fuel, but they're not used in internal combustion engines as they're too viscous. So this idea of being too viscous is a common theme.
Yeah. What was my voice? Because it's just bad for the engine overall, and it would be a bad idea to use it. So what we do instead is this process called transesterification, where we take the really long fatty acid chains of the vegetable oils and then kind of swap them out for shorter ones from the alcohols that are used in these reactions so that they become less viscous and a little more usable. And then just really remember this formula right here is something that you want to do.
This is the key formula, and this key formula demonstrates how transesterification between an ester and alcohol with a strong acid or a base catalyst produces a different ester.
Yeah. And then over here is a more in-depth explanation of how transesterification works. You don't really need to know all of this, I don't think, but I'm going to walk you through it anyway and skip over. So here in step 1, you can see how there's the hydroxyl ion from the base catalyst that is causing, essentially, all of this to happen. So you've got your hydroxyl ion, and then your alcohol with its R double prime alkyl group. And essentially the hydrogen, the proton on the alcohol, is breaking off and joining the hydroxyl group in this water molecule, which leaves the R double prime alkyl with just the oxygen. And then that is used in this next step, or phase, I guess, right here. And then here you have the ester. Notice how it's got the double bonded oxygen and the other R prime group that has an oxygen bonded to it. So what happens here is the double bonded oxygen breaks off one of its bonds and becomes a single bonded oxygen instead, which frees up a space for the carbon to bond with the deprotonated alcohol, essentially. Sorry, Darren, is there something?
Oh, no, I'm just agreeing.
Oh, nice. Awesome. Yeah. And so notice how the carbon still has 4 bonds, but now it's tetrahedral instead of trigonal planar, going back to those electron domains. Yay. Oh, God. And so here, the oxygen really doesn't like having that negative charge, and so it's joining back and getting that double bond again. But in order to do that, because if nothing else changed, the carbon would end up having 5 bonds, which it can't really have in this case. And so the original R single prime, that bond with the carbon breaks off, and so afterwards you get this, which is an ester again, except instead of the R single prime, you have the R double prime, and you have the R single prime alkyl group over here alone. Now that one comes down to phase 3, where, if you remember from before, there's that water molecule, and now what happens is essentially the first phase, but in reverse, where the hydrogen atom breaks off from the water molecule, creating another alcohol and leaving a hydroxyl ion, which is also found there.
Yeah. So ultimately, the key takeaway from this slide is that, as we mentioned before, if the oil is too viscous, the diesel engines can't really process it. So transesterification with the ethanol or methanol produces oils with lower viscosity that can be ultimately used in diesel engines.
Yeah. Alcohol has more uses than. Yeah. Transesterification of vegetable oil into biodiesel. And so this is really just an extension of the process that we just saw. Because if you notice here, we've got those are essentially esters, but together they're a triglyceride because there's 3 of them. And then here we have the 3 alcohol molecules. And then they swap, and essentially what we've got here is 3 alcohol molecules joined together called a glycerol. And then the fatty acid and esters over here join up like this, and you end up with shorter esters. Well, methyl esters, sorry. And glycerol.
Yeah, and so the key takeaway from this slide, according to IB, and I quote, is in the transesterification process involving a reaction with an alcohol in the presence of a strong ester base, the triglyceride vegetable oils are converted to a mixture mainly comprising of alkyl esters and glycerol, but with some fatty acids.
Yeah, so it's not complete, which is why even though right here we have a single arrow, it's a little more of a double arrow where things are just kind of floating around in a mixture of different concentrations.
The reaction isn't really complete, but...
Yeah. Did we mention the catalyst? Yeah, we did. Strong acid or base. Yeah. And so here we have advantages and disadvantages of biofuels, but in the curriculum it doesn't explicitly state that, but it was found in both the Cambridge and Oxford textbooks, so we thought we may as well cover it. Not saying it out loud, though, because you can really go through this on your own.
Yeah, and it's pretty much inferable, too, and quite understandable, because this is how we apply it to real life and how we interpret it like that.
Yeah. And that's about it for the content, really.
Yeah, so we wanted to go over...
we thought we'd go over one of the questions. We thought C4 question 6 was pretty good. Oh, here we go. So it says, identify from section 35 of the data booklet which of vitamins A, C, or D is most likely to appear as a colored compound, and explain your answer. So I'm going to pull up the data booklet here. And so we have vitamin A, we have vitamin C, and this is really horrible. Hold on. There we go.
And
vitamin D. And so if we start with vitamin A, I suppose, we can go through and highlight 1, 2, 3, 4, 5 double bonds, each with a single bond in between. And so that's a conjugated system of 5 double bonds. And then if we go over to vitamin C, we have 1, 2. So I think we already have a good idea of where this is going. And then vitamin D has 1, 2, and 3. And so looking at all 3 of these, vitamin A clearly has the longest conjugated system, which implies that it would be the most likely to be a colored compound. However, if you remember from before, usually it's considered a compound is considered colored if it has about 8 conjugated double bonds. So really, none of these are truly colored. Yeah. Is that it?
I think that's a pretty good place to stop. That pretty much covers an overview of C4, solar energy. And we'll be returning. And so we'll be returning very soon to cover C7 with you.
Oh, God.
Which is the fusion and fission HL section. Thank you so much for coming to our TED Talk.
Comment below what you think we should do and what we definitely shouldn't do for C7.
Don't forget to like and subscribe. See you soon.